All right, I'm back in the PHPP, so let's take a quick look at the peak heating load. So I'm here in my verification worksheet, and if we were to scroll down a little bit here, we get to our results section, and as we've talked about, we have a top-line result here for the heating energy demand. The energy needed over the course of the entire winter period in order to keep the building at a comfortable set point. In addition to the energy demand, though, we also have a result here for the peak heat load. So the peak heating or the energy demand is looking at the total energy consumption over the entire winter period. The peak heat load here is looking at performance under the worst case, most stressful moment in time for that climate. So we can take a look at the results for the peak heat load and how this number is derived by taking a look at the peak load or the heating load worksheet. So if I scroll over here to the right, we've already talked about how we have this annual heating worksheet, we have this monthly heating worksheet, and we also have the heat load worksheet. So if I go to the heat load worksheet, it looks very similar to my annual energy demand worksheet with just a few differences. I'm trying to zoom in here so we can see a little better. So as with before, we are sort of broken down into various panels. We have a first panel here for our transmission losses. We have another panel here for our ventilation losses, etc., etc. And if we notice, it looks very similar, right? We have our area times 1 over the R value times our temperature correction factor. But then notice we don't have a G sub T. Instead, we have two different outdoor temperatures, or excuse me, temperature differentials. So these are delta T values, differences in temperature between the outside and the inside. And if you look up here at the top, notice we've got two weather conditions. Weather condition 1 when it's 14 degrees outside, weather condition 2 when it's 24 degrees Fahrenheit outside. Where do those numbers come from? Well, they all come from the climate data. When we loaded the climate data way back when, these values were part of our climate data set. And so using these values, the PHPP can go off and calculate a difference in temperature between the inside and the outside. And remember, with the PHPP, the way it works is that we don't know whether weather condition 1 is our most stressful condition or if weather condition 2 is our most stressful condition. Now, you might look at this and you might say, Ed, that doesn't make any sense. Obviously, weather condition 1, 14 degrees, is more difficult, is colder, is more severe than weather condition 2. And that's true, except that when it's really cold and really clear, we will have a lot of transmission losses because it's so cold. But notice over here that we will also have much higher solar gain. So we will have a lot of transmission loss, but we'll have a lot more counterbalancing solar gain. And so we don't actually know which of these two weather conditions is the most stressful because we have to take into account the outdoor temperature, but we also have to take into account the solar radiation. So that's what we have here. We have 1 and then 2 weather conditions, and so then 1 and then 2 total transmission heat losses for the peak condition. And we'll do the same thing for our ventilation. So we'll calculate the ventilation losses for weather condition 1 and the ventilation losses for weather condition 2. Then we'll total up the total losses for weather condition 1 and the total losses for weather condition 2. And then we'll take a look at the gains. So we'll first calculate solar gain for weather condition 1, then solar gain for weather condition 2. Notice very different in this case. Internal gains will be the same for both cases, and then as a result, we get 2 total peak loads. And in this case, notice that the peak load for weather condition 1 is actually about 200 BTUs per hour larger than weather condition 2. So therefore, that becomes our limiting or our peak heat load. So about 6,000 BTUs per hour, about 1,700 watts or so. If we then divide that by the TFA of the building, we get our specific peak heat load. And we would then compare that to the maximum amount of energy which is transportable by our fresh air ventilation system. If we notice down here, we see that we at most could supply about 5,800 BTUs per hour of heat through the ERV, through the HRV, based on its flow rates. And therefore, we can't actually heat our building through the ERV. So in this case, we are not actually able to heat our building through the ERV or the HRV. Notice 4.27 is higher than 4.22. So obviously we won't be able to heat our building using this supply air. We can get close, but we can't quite supply all the heating for that peak condition. Now, as I've said, that's sort of academic. We wouldn't really want to do that anyway in this case because we're already buying a heat pump to provide all of our active cooling. So why wouldn't I just use that to provide all my heating as well? So certainly you could try and improve performance to get down below this threshold if you wanted to, but it's not going to, I don't think, affect you too much. Now, if you were in a dry climate, if you were in a climate that didn't need active cooling, then maybe this would be a reasonable thing to shoot for. Although you still have a lot of controls challenges when it comes to a system like this. So it's not always a sure thing, even in certain climates. Even if you are able to do this, it might still not be the simplest, most efficient or effective, I guess, heating system design for your building. So, keep that in mind, take that into consideration. But as I said, the PHPP does have some nice tools here to help us evaluate this peak heat load, see if it is something that we want to consider. So there's our peak heat load. We've also talked about our annual energy demand. And of course, in previous lessons, we've talked about our cooling energy demand. We also have additional worksheets here for things like cooling energy demand. On our cooling worksheet, it looks just like or it looks very similar to the heating energy demand. And then we have another worksheet here for the peak cooling load, sort of the opposite of the heating situation. So we have similar worksheets here that allow us to take a look at the cooling energy performance and the peak cooling load performance. Very, very similar. You see here 2 weather conditions. We have all of our same sort of surfaces broken down. So the PHPP gives us a tremendous amount of data about both our heating energy demand and our peak heat load, as well as our cooling energy demand, as well as our peak cooling loads. And of course, we have seen in previous lessons how we get a lot of information around overheating and our summertime passive cooling performance as well. So a lot of results here that we are able to look at for our building. So let me go back to our verification worksheet. So does that mean that we're done? Does that mean that we've got everything modeled in our building and we are now a certifiable passive house building? We are meeting the heating energy demand limits. We're not meeting the peak cooling load, but that's okay. We don't have to. We can choose either of these 2 for certification. So we can just sort of ignore this one. We can kind of turn that one off. We are meeting our cooling and dehumidification demand, notice over here. And for certification, we don't have to worry about cooling load in this case either. We are meeting our frequency of overheating and our frequency of high humidity. We are meeting our pressurization tests. So notice we've got a whole bunch of yeses over here until we get to the bottom, until we get to this last section. So we're almost there. We're almost done, except that the last piece that we need to input, the last piece we need to model, has to do with the primary energy for the building. So let's turn our attention now to the primary energy and see what it's going to take for us to finish up our PHPP model by completing the primary energy inputs.